Thank you very much for attending. As I'm sure some of you are aware, Kubernetes at the moment is gaining a lot of excitement, a lot of traction within the community. And people are very keen to explore how we can change the way we're deploying software and how we can improve and introduce more resilience and reliability into our deployments. And this is what I want to focus on today. But in particular, how do you do that when you're deploying existing Windows applications and working within existing Windows applications, and how does that look like when we want to use cool, new, shiny technology like Kubernetes? But at the same time, we'll also cover if you're building .NET Core and .NET Core and Linux, how that works on Kubernetes, and fundamentally, how can we get the most out of it? What will it bring to our companies if we decide to adopt it and bring it into our stack? So my name is Ben Hall. I am based here in London, and I'm the founder of a project or company called Katacoda. Katacoda is an interactive learning platform for software developers. So directly in your browser, you get given pre-configured environments with Kubernetes clusters or OpenShift, or in this case, Docker. And alongside that, you get step-by-step instructions about how you can solve particular problems, like how do you deploy Kubernetes, or how do you deploy and configure applications running on top of it. And it's all available for free. So after you've heard all about these awesome technologies I want to explain, you can go and try it for free on Katacoda without having to download or install anything. So as I introduced, I want to start with an introduction and provide the fundamental foundations into how do you build these new Windows containers, what makes them different to Linux, and why am I excited about the possibilities. We'll then take those containers and we'll deploy them onto Kubernetes. We'll look at what Kubernetes brings to the party and why everyone is getting so excited about the possibilities it's bringing. And because we're dealing with production and we're dealing with infrastructure, we'll look at actually what does that look like in reality? What are the day-to-day operations that you're going to be concerned with? And how do you manage things like monitoring and making sure that your applications are working when you're deploying into these cloud-native-based solutions? So I'm sure that many of us have explored and played with Docker so far, but for those who are coming into the topic fresh, containers allow us to take complex software, which can be off the shelf and configured by vendors, or what we've built internally in our own applications, and package it up and launch the process. Docker fundamentally is a process manager. When you start that container, all it's doing is starting the Linux process or the Windows process or Windows containers, and making that available, exactly as if we installed the package and ran it directly. The main benefit of that is how they keep it secure. So they use certain features within the Linux kernel to make sure that they're sandboxed and separated and isolated from other things running on our machine. And that means that if something goes slightly corrupted or malicious, or they accidentally get hacked into, they can't interfere with the rest of the system. They can't take things down, and they can't breach and attack other parts. What it also means is because we've got these containers, they get packaged up as these Docker images. And these Docker images contain everything what that process, what that application needs in order to be able to start. So in the case of this example, we have SQL Server. We've got the new version of SQL Server that had been recently ported over to Linux. And as part of that, it will have the SQL Server packages. It will also have a base operating system and all of the files it needs. So, for example, Debian or Ubuntu or CentOS if you're interested in more of the Red Hat side of the community. And it has the configuration by default set in and everything you need. So now if you want to launch SQL Server on Linux, you would do Docker run. This will launch a container. You set some nice environment variables because it is still SQL Server after all. So we accept the end user license agreement. We set a nice secure password. Open up the port so we can access it. In this case, the default port for SQL Server is 1433. And then the name of the image. And if it's not on our machine already, we'll go off and download it. And once it's been downloaded, it will launch the process. And now we have a full version of SQL Server running. And so this provides us a lot of benefit and a lot of advantages. But it's not just web processes and databases that are beneficial and helpful when we're dealing with containers. We can also just run day-to-day development tools. And we can run them, for example, the Azure command line. We can launch that directly from as a container and as a containerized process. And so we don't have to worry about how do you install it, what versions of Python do you need, what's the different configuration, will it interfere or upgrade other things running on my system. Instead, we launch out the process, we solve the problem we need to solve, we stop it, and it can get completely removed from our machines without any side effects or without anything left behind. And so this helps us move and change and experiment with different technologies a lot more effectively. But for most of the time, the real benefit is when we want to deploy our own applications as a container, and we want to deploy what we're building in a more streamlined, more standardized, packaged up way. And so instead of worrying about different versions of .NET being installed in development teams' laptop, to staging and build agents, to production, by having everything packaged up at this Docker image, we can streamline that, and we can be confident that what we're building and testing against is actually the same exact version as what will be running in production, no matter where it's running, whether it be bare metal, cloud, or hybrid type solutions. And so in this case, I'm going to build a very simple Hello World application as an ASP.NET Core. It's going to be targeting Linux initially, and then we'll look at Windows. But the application is quite simple. It returns the machine name. And so in this case, when you launch a container, the machine name of which the application thinks it's running on is the name of the container itself. And so when you're raising error messages, if your application does happen to have an unfortunate event, by tracking the name of the machine helps you track down to the container which was actually running it, and so it's a helpful trick for debugging. And so in this case, that's what I've been focusing on. The second important part of a containerized application is the IP address which the application is listening on. So by default, certain applications will listen on 172.00.1. And so they will only listen for requests coming in on the local loopback network card. And so this makes sure that things from the outside can't accidentally access it, which is very nice and very secure. But when we're in a container, obviously the network, well, not obviously. When we're in a container, the network interface for the container is not the local loopback of our host machine. It's in a different network interface. And so if it's only accepting requests from the local interface, it's only accepting requests from within the container, because everything is sandboxed and everything is isolated. And so what we need to do is actually, within our configuration, be very explicit and say, like, actually, please listen to all IP addresses and requests from all available network cards and network interfaces. And in this case, that's done by binding to 0.0.0.1. And this allows us to receive network traffic from other containers and other parts of the system. A very common problem, which I spent many hours debugging about why my application isn't responding to everything, and that's just because it wasn't on the right IP address. So two key things to be aware of when you're looking at containerization for apps. So now we want to start taking this application and turn it into a Docker image. Once we have this Docker image, which defines the structure of the application, we can start it and turn it into a container, which is just a running process based on that image. And so to do this, we need a Docker file. A Docker file is a list of instructions which define what our application needs and how it's been built. So in this case, we're defining our base dependencies. We're saying we want .NET, we want 1.1.1, and we would like the SDK tooling. And so based on the naming convention that Microsoft produced when they produced their base Docker image, that is the name which we need to define. And so this has got .NET already installed, everything configured, and so we can use that and then be confident that we have all of the tooling we need in order to be able to successfully build and publish our binaries in .NET. And so in this case, for .NET, we have .NET Restore, which will pull all the packages in from NuGet and pull them into our container. We copy over our source code into the directory, and then we can run .NET Publish and build our nice DLL. Two critical things at the bottom are some metadata about how the application is functioning and how the application is configured. And so the first thing we do is say what port the application is listening on. And so when this image is being run in production, this metadata, this expose, can be interrogated and it can be used so that people don't need to figure out how the application is configured. But it also helps things like Kubernetes understand the structure of your application. It can use them to infer that and help it by automatically configuring different requirements. And then finally, at the bottom, we've got the default command, i.e., how do you launch this application? And by having this baked into the image, it means that we can be less dependent on the actual underlying technologies, and instead we can focus on a much higher level abstraction, i.e. run this container. And then the container and the image has all of the information it needs to work out how to start the process. if we had to document that on every single time we launched a container, we'd have to be very aware about, okay, what's the name of the DLL? What even technology is actually running inside of that container? Is it Node? Is it .NET? Is it Golang? By having that all packaged in, we just are concerned with the abstraction of like, here's my application, here's my image, please launch that somewhere. And so these are the techniques when you're building it. And so when you have that Docker file defined, they look and feel consistent between different applications. You turn it into an image by doing Docker build, give it a nice friendly name so you can refer back to it later. And Docker will run through all of the steps within your Docker file, which will then eventually get you to your nice built running application, which is ideal. And so now we have something which we can run and something which we can deploy. The one issue with this at the moment is, you may remember in my Docker file, I defined the SDK as my base layer. And so at the moment, when I go to run this in production, I'm actually also running all of the SDK tooling which went with it. And this has some potential security implications, i.e. if anyone broke into my web app, they'll be able to compile their own source code and then be able to compile their own applications or utilize additional tooling which may be left behind, like curl commands or wget, and as such, use those to exploit it. And we don't want to make it too simple for attackers. We want to at least then make them work for their exploits. And so we can simplify and we can reduce the size of our images and get them ready for production. And so Docker's introduced a new concept called multi-stage builds. And this is where we can change and add a secondary stage to build a more optimized version of that Docker image. And so we have our first stage, which is what we had before, which was using the SDK tooling to build the DLL. And then as a second stage, what we can do is define a different base image. So in this case, the runtime, so it doesn't have all the compilers and doesn't have all of the additional tooling. We can copy our DLL, which we built using the first stage, the first set of images, and using the SDK, and into our more optimized version of the container image. And by doing this, we reduce the size. We take it down from 900 meg because it's got all that compiler and additional tooling in, and we make something much more secure and much more optimized, which is only 250 meg. And we can continue optimizing and building that. And so it's a really nice way to get our images ready for production and ready to deploy onto something like Kubernetes. So that's how it works in Linux. So what about Windows? And how does Windows change matters? So as part of the Windows Server 2016 release, there's 4 key components which were introduced. We have Windows Server Core and Windows Nano. These are operating systems designed for running inside of a container. And so we can use this, exactly what we did for Linux, where we defined the SDK. We can use these as our base foundation and then build upon and deploy our applications. And we also then have introduced 2 new container runtimes, Windows containers and Windows Hyper-V containers. Windows containers are very similar to what we experience on Linux today. So they share the host kernel, but when you start that process, it will start the Windows process underlying, and it will still run in a very sandbox, secure way, very similar to how it runs on Linux. But like on Linux, it will utilize and share the kernel of the host. And so all of the machines, all of the containers on the machine will all talk to the same kernel. And so if you did unfortunately have a kernel exploit, potentially it could interact and interfere with all of the different other containers. This is where Windows Hyper-V containers adds an additional isolation mode for our applications. And so when we launch it in this Hyper-V isolation, what happens is that Windows will boot up a very similar, small, lightweight virtual machine, and it will run that container within the virtual machine. And so we don't have a shared kernel issue. It's an isolated, standalone kernel wrapped in a VM. And so if anyone did manage to break out, they would only hit the VM, and then they would have to break out of that. But that's already been locked down and super secure. And so it's an extra defense and an extra barrier without any performance overhead. But when we launch these containers on Windows, they look and feel very similar to Linux. So we've got our server, an operating system, we've got Windows, we've got Docker, and then we can run things like SQL Server or IIS from the Windows build, from the Windows packages, directly as a container. When we look at Hyper-V, as I said, the difference is that the kernel is separate, it's isolated based on this super small Windows utility VM. And we can see where this is beneficial of things where you're potentially running slightly more third-party or potentially malicious code. So shared hosting, i.e. if you're Azure, you probably don't want people to be using the same kernel just in case people are out to purposely target the other things, and multi-tenancy. So if you're running 2 government departments, you probably don't want them to interfere and interact if they're from different governments, just for that added benefit. And other particular reasons. But fundamentally, Windows containers are still secure, safe, reliable. There's 2 new operating systems. So we start with Windows Server Core. Windows Server Core is nearly Windows 32 compatible. And what I mean by that is it's got all of the same APIs you would know and love from Windows. And so the idea being that you can pick up your application, it doesn't need to be changed, it doesn't need to be rebuilt, and it will almost run without any modifications. And when I say almost is, there's some APIs which they couldn't quite port over. There's some things they have removed, like the fax server, which, to be honest, is probably acceptable. But the idea is that it will be the same experience, and you can just literally take your VM, turn it into a container image, and then run that on Server Core. Windows Nano is the really stripped down, really lightweight version. And so this has gone through a few different iterations and a few different processes. Windows Nano originally was meant to be a lightweight virtual machine that you could boot up on Hyper-V, and it would be, have a low footprint, and so you could pack it more effectively and get more value from your resources. But that's been changed recently. People weren't utilizing that, and as we moved into a containerized world, Windows Nano is now designed just for solely running inside of a container. And this means that they could remove all of the logic about how do you actually boot the VM in the first place. And now Windows Nano is approximately 50 meg in size. So really nice base footprint for packaging and deploying our applications onto. And so when we look at where this means and what this means for us, Server Core is kind of like your traditional operating system. It's got all of the APIs, it's got all of the legacy functionality there. And the idea is that you can lift and shift, and everything will just work as it was. Very similar to if you start packaging up applications as containers on Ubuntu. Windows Nano is more aligned with something like Alpine. It's focused on being run as a container. It's focused on not having complete 32-bit compatibility. But for 90% of the applications, that's probably fine. And you can get a much more effective, much more cut-down version of the runtime to build your applications on. But you may have to do some tweaks and some modifications or rebuild it to get the APIs compatible with that. And so now, once we have this, we have the ability to package up and build our traditional .NET Windows-based applications as containers. So what does that look like in reality? So let's take a way back into the great early days of .NET, where the ASP.NET team were producing different examples, and one of the examples was something called Nerd Dinner. Nerd Dinner, in this case, is hosted on Coblex until Coblex gets turned off. And this particular build was released in May 25th, 2010. So it's like one of the earliest .NET examples I could find. And fortunately, it's been built and it's been packaged up in a zip file. All the binaries are there. But how can I now take that and package it up, and what are the changes which would be required? So we need to be able to deploy and build our Windows containers. So now we've got Docker. Docker works natively on Windows using some awesome Golang functionality. But the Windows functionality is piped into the core of Docker. It's not a fork, it's not a spin-off, it's not something driven by Microsoft. It is part of the main Docker pipeline. It goes through all the same testing, all the same CI integration points. The idea then is that we have two binaries, multiple binaries, Windows, ARM, and Linux. And so you install it, and you can run it, and you've got all your container images. And just like what we do with Linux and what we had with the .NET SDK, there's various different base images which have been built, which we can use as our foundations. So this is the base images for Windows, and you can see that all of the tags on the far side are all of the Windows build version numbers. Because when we have Windows, we also have Windows updates. But we can't just have things randomly updating itself within a container, because that breaks the whole repeatability and knowing what's actually running inside of production. So instead, we've tagged things with the Windows build, and so you know exactly what version of Windows we are running and what version and security updates have been applied. And so when we do that, we've got images. When we try and run something, like in this case, Windows Server Core, it will get downloaded. And when something gets changed and a new security patches have been released, we only have to download and pull the changes which have been applied as an additional layer. And so we don't have to keep downloading these huge images every single time. Instead, we can keep things a lot more focused. So just like we had before, and just like through the same example, we now need to build a Windows-based image. And so we have our Docker file, and now we have our base image. So in this case, Windows Server Core. And on top of that, we can run Windows-targeted commands. In this case, install feature web server, so I install IIS. And we use the same functionality, the same syntax, the same approach, but now we're building something which is targeting Windows and using the Windows functionality and the Windows kernel to bootstrap it. Fortunately for most of us, lots of base images, so IIS is already available, lots of different versions available, some for Windows Server Core, some for Windows Nano, and we can use and build upon that in our application. So now when we're trying to build and deploy this Nerd Dinner sample application, what we can do is just use the official IIS image from Microsoft, we give it the Windows build which we're interested in running, and use that as our foundation. So now we can be confident that IIS has been set up and configured as we need. Same things, we install the dependencies, so .NET frameworks, we can configure IIS within our container, and so we remove the default website, we create a new one for our app, we tell it what port to listen on, and at the same time we give it that metadata, and finally copy in our binaries. And so fortunately, everything had been pre-built by Nerd Dinner, so all we need to do is really configure the syntax and configure the IIS infrastructure as part of our deployment, and that's what we're doing here. And then the application will hopefully just launch. So as we did before, we do a Docker build. This will run through the steps. It will configure IIS. So when our process launches, it will launch IIS in a configured state what we desire, and then when we run it, our applications will display. And so by taking an application which has existed without modifications, because we've got that Windows Server Core base image, and because that is compatible to Windows, we can just pick things up and put them into production. And then once we're at this point, we can look at optimizing and reducing the footprint with Windows Nano, etc., and getting into something much smaller. But at least this is our starting point to have something running, whether it be Linux or Windows-based images. So now we are getting to the point of how do you actually run these and what's required to run this in production. If we're just doing Docker run on a VM, we'd have to log in, we'd have to connect, randomly run commands on a command line, and it will eventually get to the point where it becomes unmanageable and mistakes will start to be introduced. So what we want is systems which are designed to manage these containers for us, and if things happen, automatically adjust and automatically react to the state of our system and state of our infrastructure. And so there's many different approaches to orchestration. There's Swarm from Docker, there's OpenShift, there's Mesos, there's DCOS, there's Cloud Foundry, but the most popular one, or the one which is getting traction from the community, is Kubernetes. So the official definition of Kubernetes and what it is an open source system for automating, scaling, the management of containerized applications, i.e. the things which we have just built and we need to now push into production. And Kubernetes was born from inside of Google. So Google run all of their systems as containers. They have done for the last 10 years, and they have provided and pushed back a lot of the core infrastructure and a lot of the core technologies into the Linux kernel, which keeps containers secure and are the things what Docker is building on in the first place. And so they have a huge amount of experience in knowing how to operate containerized systems. And so they have Borg, which is their internal version of how they do this. They published a white paper, and at the same time, they also started work on Kubernetes, which takes their internal experience and makes it available to the wider audience and companies who aren't just Google. So this has been awesome and really captured experience and knowledge and transferred that in an effective way, not just through blog posts and technical talks. And the premise of Kubernetes is to take all of our containers, no matter what types of containers they are or what purpose they're serving, and be able to organize and manage those in a nice, simplistic, consistent approach. And to do that, we need various different functionalities, and we need various different features, which is provided by the base structure. And so these are a few things that I've pulled out, which I think are critical when we're thinking about how do we run and manage things in production. So we've got aspects like role-based access control. So being able to specify which teams and which people and individuals can manage which components of our applications. So who can deploy Project A systems, or who can manage and view the state of that, and making sure that Team A can't interfere and interact with Team B's workloads. We also have things like self-healing. So if something happens at 3 a.m. in the morning, we don't want network operators and infrastructure teams to have to go in and manually update and manually fix whatever problem we want. It's much better if our systems can start self-healing and self-fixing and correcting the problems. So if we lose a server or if we lose a data center, Kubernetes will detect that, and it will automatically reposition whatever systems and whatever aspects of our workload, what was being deployed, onto other parts of the cluster. And so we don't lose capacity, we don't lose availability, and Kubernetes is always making sure that that the capacity which we've defined is always available. And so we don't have to go in and manually intervene. We have other things like being able to manage scaling and rollouts and rollbacks, managing secrets in a secure way so that we're not randomly leaving passwords or certificates just on a disk or in an environment variable somewhere. Instead, they can be backed by an actual secret store. And finally, the one which I think is often overlooked is batch execution. By default, we think of containers and we think of deployments as these long-lived, long-running processes. Like we want to deploy a database or a web server or a message queue. But actually, there's lots of different types of workloads which we have. We have one-off cron jobs, which need to run at 3 a.m. every morning to recycle something or run a type of report. And we also now are starting to see more big data workloads. So being able to go like, we need to be able to process 1,000 different images, classify them, and then return the results or upload the results as part of a report. And so Kubernetes is designed for managing scheduling and execution of workloads. And that happens whether it's long-lived running processes, which may go down and have to be recycled, or one-off jobs which run for 10 seconds and then disappear and then never run again. So as part of Kubernetes, what has actually been introduced and what has been developed is a really advanced object model which represents all of the different moving parts of an infrastructure and a production-based system. And so at the heart of Kubernetes are concepts called pods. Pods are fundamentally containers which are running our workloads. And so they can be Docker containers or different types, but they are the containers. Around these pods, we have different services. So we have things which are managing the schedules and how these pods should be executed. So for example, a daemon set will automatically run the pod, i.e. the container, on every single node within our cluster. And so we have services such as monitoring that must always run on every single host so we can collect and return metrics. You would deploy it as a daemon set, and then when Kubernetes identifies and introduces and detects a new node being added, it will automatically go ahead and deploy the monitoring code and make sure that it's running. And so we have these guarantees in place, and so that we don't have to go through a playbook of what needs to happen when we add a new node into a cluster. We then got things like stateful sets, which are designed for running databases and stateful applications. And so as we scale up our database, certain things need to happen, i.e. they need to point to different directories. Because if they all pointed to the same directory, they'll conflict and they'll fight and they'll override data. And so when we scale up and we think about multi-tenancy and multi-node systems, we want to make sure that they're scaling appropriately. And then at the bottom underneath, we have obviously our core foundation. So we have volumes, so our container can store data, and it can store it in different ways. It could just be a directory on disk, or it could be certain things like secrets or configuration. And Kubernetes has objects which make that easy and make that manageable from our viewpoint. So we can focus and configure the right objects based on what problem we're trying to solve within our system. And so when you look at what gets run, we have these nodes within our system, and then everything which we want to deploy, like all of our applications, be that the Nerd Dinner app, which we just built, will be deployed as these pods. Now, all of our IP addresses, but within that pod, we can configure it, and we can tweak the actual implementation details of that. So if it needs to be made up of multiple different components and multiple different containers, we can package them together as if they are all running from within the same interface and same container itself. So they all share the same IP address, they all share the same volumes, they all look and feel as if they're together, but from a development experience, we can break it down into small, isolated components. When we want to scale, these pods get scaled together. And so when we want to bring up a part of an application, all of the volumes and all of the containerized apps within that will get scaled up and added together. But the second important part is not only does Kubernetes need to manage started applications, it needs to make them available. And so Kubernetes has got different approaches based on how to configure and how to manage networking. The three ones which are most commonly used are node ports, cluster IPs, and load balancers. So a node port is the ability to allocate a hard-coded port across your entire cluster. And so no matter what machine you're accessing or data gets received on, it will always get routed to the correct pod, which may be on a different part of the system. And so you can always make systems available as they get moved around. Cluster IPs are an aggregation IP address which manages load balancing across different components within our system. And so this gives us a single IP address which we can send traffic to, and then under the covers that may get distributed to different components and different systems for reliability and scaling out our workloads across different machines and different nodes. And then finally, load balancers, which are concepts which will automatically configure a load balancer based on the cloud provider which you are utilizing. So if you deploy Kubernetes into Azure or EC2 and you request a load balancer, Kubernetes will go off to Azure or EC2, get and configure the load balancer and the ELB, for example, get allocated a public IP address, and then make that available within the system. And so when traffic gets sent to that public IP address, Kubernetes will manage in how that gets to the underlying pod, the underlying workload that we're interested in receiving traffic. And so I borrowed some awesome slides from our friends over at Weaveworks to kind of help illustrate this in a little bit more of a colorful way. So traffic comes in on node port. It doesn't matter which node within our Kubernetes cluster traffic is received on. It will come in and it will know which pod is responsible. So it will forward the packets over the internal network to the most available pod within our system which is available. Similar to cluster IP addresses, when we are within our cluster, and let's say our web application, our Nerd Dinner sample app needs to talk to SQL Server, it will go off to in the DNS service, it'll go like, where is SQL Server running? And this will return back, he's got 3 instances of SQL Server running. Here is the one IP address which represents all of those, and it will send traffic to that and forward it on, and then the traffic will go to our pod. And then finally, load balancers, which, as I said, it will automatically configure the load balancer via based on the cloud. And when traffic comes in from that external load balancer, it will help manage and introduce that into our cluster. And all of this is managed and configured via code. And so this is awesome because now we're no longer defining bash scripts, we're no longer creating these complex, confusing playbooks to get our system into a state where we desire. Instead, we're defining how we want the objects to be configured, and then they understand what's required in order to make and deploy our applications based on what we've defined. So in this case, we're configuring a deployment object. We're giving it some nice friendly names so that we can understand it, and we're setting a label so that we know how other parts of the system can connect and interact and build upon what's been available. And then finally, the spec, i.e. the workload for this deployment object is containers. And so we define which container we actually want to be running within our system. And all parts of Kubernetes is configured via these YAML definitions. And so in this case, we've got our service, i.e. how do we want to make our front end, our Nerd Dinner application available? And so in this case, we're using Nerd Dinner, and we're defining what node port should be. And so whenever traffic comes in on 30,080, it will always get routed to the right available front-end application. And it knows that it's interested in directing it to front-end because at the bottom we've defined our selector, i.e. we've defined what labels should be used and identified and send traffic to automatically. So this is for Windows. What about for Linux? What about for Windows? So we have exactly the same structure. We have exactly the same configuration. Instead of defining a Linux image, which has been built, we can find a Windows-based image. They look and feel identical, and that is important. The only thing what we need to tell Kubernetes is we need to give it a hint about where we want this workload to be running. And so in this case, the workload needs to run on Windows-based systems. And so when we deploy this object and we want Kubernetes to schedule this workload, what we do is define a node selector. And we say, please select nodes which have the label operating system Windows. And so Kubernetes will take that into consideration, and it will only schedule it on nodes within our cluster which have the label Windows. And as such, they have Windows containers, and they can run our workloads. And so we can have our IIS application working. But before we get to that point, we actually need a Kubernetes cluster in the first place. So how do you go about doing that? So there's two key components to setting up and configuring Kubernetes. First one is you need a master, and then you need nodes. The master is responsible for scheduling, managing the workloads, making sure that the state of our cluster and state of what's being deployed is actually how we want it to be. And so if things go down, it will be the master who will detect that and then reschedule and reallocate our resources. And if we want to deploy new components and new deployment objects or update them, we go to the master and we tell it, please schedule this operation to happen, and that will manage it. All of the heavy lifting, all of the workload is done on nodes. And so these nodes have our container runtime, they have all of our networking configurations, and they actually are the things which do the heavy lifting. And so at the present, we have these two types. Our master can only be Linux, so we need to be able to run Linux systems, which is configured and will run the master. But when it comes to where the execution's happening and where all of our workloads are being done, this is now cross-platform. And so we can run it based on Linux, we have Windows, we have ARM, and as more different architectures get introduced, more different architectures can be added. And so this is how we can now have a single Kubernetes cluster which is capable of running different types of workloads based on the underlying architecture, whether that be for Linux or whether that be for Windows. And so based on how it's all been configured, they can also communicate transparently in this hybrid approach. And so we could have Nerd Dinner running on Windows containers, utilizing Server Core, which has never been modified, talking to Windows Server Linux, running on Linux containers, on a Linux host, all over the network, all on different machines in our cluster. And Kubernetes will manage that workload and how that happens. But Windows has a little extra thing up its sleeves. So Windows, they recently introduced the concept of Linux containers on Windows. And so what Microsoft and Docker are building is the possibility that not only can you run Windows containers on Linux, but you can also natively run Linux containers on Windows. Through the powers of Hyper-V and virtualization and other magic, awesome things that Microsoft are currently building, the experience, which I stole from a screenshot from DockerCon, is you can run your containers as we've shown, i.e. just do Docker run Nano server, and that will run via Windows. But you can then take a Linux container, i.e. Alpine, and run it in exactly the same way, and let Windows figure out what is that responsible for. And so now when we look at how do we manage that with Kubernetes, Windows actually starts to become a really nice choice for running all types of our workloads, no matter whether that's Linux or Windows. And so Kubernetes will be able to schedule containers of both types and both architectures on our machines. And so we can start utilizing and repurposing Windows in a lot more of an effective way. So this makes it a really good platform. And so in order to configure and build our Kubernetes cluster, we need a way to do that. And so one way, which I really like, is kubeadm. Kubeadm init will initialize the master. So on your Linux box, you would initialize the master. That will go ahead and it will configure all of the components, set up all of the certificates that was required, and give you a working master. And so then on each node, whether that be Windows or whether that be Linux, you go ahead and you join a cluster. You give it a token so that only valid nodes can be added into the machine. And then Kubernetes will take that and start scheduling workloads onto the two of them. And so when we say, like, what nodes are in our cluster, we see all the different types of architectures and all the different types available, be that Windows or Linux. And then Kubernetes can manage both of those. And this is the dream, right? This gives us a single way of managing different types of workloads. The unfortunate bit is that Windows is still quite difficult to manage and still quite difficult to configure. Fortunately, all of the cloud providers also realize this. And so we have a managed way of deploying and managing our Kubernetes infrastructure. So this is managed Kubernetes service offered by Azure. Through the Azure command line, you say, create me a cluster, and it will go ahead and it will initialize you a cluster. You will then go ahead and say, AKS Kubernetes service, get me my credentials. So this will get the certificates and get all of the configuration required, store it locally, and then you can start managing and going like running commands like get nodes. Because it's Azure, they are very good at running the hybrid workloads, so both Windows and Linux machines. And so this will support hybrid clusters shortly. You can do things like what are the available versions of Kubernetes. And because it's a managed service, it takes care of all of the management of Kubernetes. And so in this case, while the cluster was initialized with 1.7, 1.8 is released in the magic of the 10 seconds before it got initialized. And what you can do is Azure will manage that upgrade process. And so you will specify then we want the cluster to be upgraded to 1.8, and then Kubernetes and Azure will work together and collaborate in the infrastructure and then slowly roll out and slowly update all of your agents, all without losing downtime and all without losing availability and capacity. Because what happens is it will go to upgrade one of the agents, it will first stop the workloads, reallocate them to other agents running within the cluster, wait for them to come back up, make sure that no other workload is running on that machine, upgrade it, make it the version which we desire, and then pull it back into load balancer, and then move on to the next agent. So Azure is a really good solution for this, but there's many other managed Kubernetes services. Kubernetes, the Google Kubernetes engine, Google created Kubernetes and have a big influence, so it makes sense that their cloud provider also has a service. And now Amazon have also joined the party and realized the importance of how do you run a managed Kubernetes service. All three cloud providers are trying to solve the same pain point, which is letting you focus on your workloads and defining the workloads that need to run and not managing and understanding the details of how does Kubernetes operate at scale, how do you make it highly available, how do you perform upgrades, etc. Taking all of that pain away so you can focus on what your applications require and how it needs to be done. There are alternatives, and so if you want a more on-premise solution, but have it in a more managed self-service style of way, there's different distributions which build on top of Kubernetes to help manage and make it simpler. So one popular one is OpenShift from Red Hat. And so this is an opinionated way of how Kubernetes should work. And so out of the box, it's got things like user authentication configured. It's got all of your build pipelines and Jenkins integrated. It's got registries. It's got all of the moving components. And it's also got a very pretty, beautiful dashboard with some nice animations so that when you need to scale up, you click the arrow up, and it will automatically spin up pods, and it will get a nice animation. It's very important when you're in the intense load to have some nice effects going on. But the purpose is, like, remove the actual day-to-day operation pain of what it takes to run Kubernetes. And so, again, you can focus on your applications and take some of the opinions that's required away. And so when we have to manage it, everything gets managed in the same way, whether you're running a managed cloud service, whether you're running OpenShift, or you've gone bare metal and built it from scratch. And so if you want to do things like make our .NET app, whether it be on Windows or Linux, doesn't matter anymore. It's always that consistent experience. And so if we want to make it available to the outside world, we can request a load balancer. Kubernetes will figure out what cloud we're in, go off to the service, get our public IP address, and then the external IP address will sit there polling and waiting until it's been assigned. And then once it's been assigned, we can get the IP address from get service, i.e. list all the services available, and send traffic to it. And so that will be managed and send the appropriate request to the services available. In this case, we only have one replica. We only have one instance of our workload happening. And so every single time we send a request, it will always go to that one available pod. But Kubernetes manages all of our infrastructure. So it now manages how we can scale up and how we can define and add more replicas. So we can use scale, we can find 3 replicas and tell it what deployment we want to scale. And so all of that configuration will be brought up based on our definition. And so now we have our 2 additional pods being configured. And because of how Kubernetes is configured, it will also automatically update our load balancer. And so when we now send requests, it will send it and round robin it to all of our available replicas, our available pods within our cluster. If one of them happens to crash, unfortunately, then Kubernetes will detect that, automatically remove it from the load balancer, and so it never sends bad traffic or valid traffic to a down part of the system. And so we ensure a much higher reliability, much higher availability, because Kubernetes is automatically configuring everything based on what our cluster is trying to achieve. And that's the same as when we roll out updates too. Like when we want to deploy a new version, Kubernetes is there to support how that actually should operate. So in this case, we're setting the image, the target of what we're deploying, to a new version, and Kubernetes will roll it out progressively. And so instead of taking down all of the available instances all at once, and so our application becomes unresponsive, instead it will do it one at a time. And so by default, with the round-robin approach, the request will slowly upgrade. And it will start with one, move on, update it, and then move it on to the next one. Because doing things like set image feels a little bit manual, again, and that's probably not where we want to be, what we could also do is just modify that object definition which we created in YAML. And then we can do a reapply. Kubernetes will look and understand the differences between what is the current state of our configuration compared to the desired state which we just said apply, and it will change and update the differences on our state to reflect that. So in this case, it would update the image, and then it perform the rolling update across our system. And by having it as this YAML definition and as our YAML file, we can start building automation. And so we can have things like our definitions, our object definitions stored in source control, and then when we do a push, then that will kick off our build, and then that will roll out, and that will trigger something. So Alexis from Weave is doing a talk on this concept tomorrow called GitOps, about how you can combine something like Kubernetes and Git together to create your automation foundation and automation pipeline. So what about private registries? i.e., if we've got our source code, we don't want it to be hosted publicly and available to everyone. We want to make sure that that's private and kept in. And this is where Kubernetes has got powerful secrets management for storing things like passwords and secure, sensitive information. And so in this case, we're just using command line to define it, but there's ways to do that with object definitions. But the idea being that our infrastructure team and operations can configure that in advance. When it comes to the purposes of using those secrets and using that information for deployment purposes, we just need to define what key and what credentials to use in order to be able to access that image. And so now we don't have to have shared passwords or password management solutions. Instead, we just need to manage what credentials we're targeting and what credentials we need to use in order to be able to achieve it. When it comes to storage, we want to be able to store stateful information. And so we can do that by, when we're defining our claim, when we're defining our YAML definitions and our deployment approach, we can define volumes. And so in this case, we're defining them as a stateful set, but the idea being that every deployment within our solution has the required volume attached to it. And so in this case, every single time we scale up and every single time we add a new replica to an instance, it will have a unique volume attached to it. If we wanted, these could be shared, but in this case, they're separate. And we have that control and that flexibility all being defined based on this object definition structure. But when we're running things like databases and storage, there's actually more concerns, and there's more human intervention required to perform certain operations, i.e., if we're running Elasticsearch and one part of the cluster goes down, we can't just bring it back in. And if our MySQL master goes down, restarting it necessarily could have some adverse effects. And there's certain human-based operations that need to happen to bring our system back up into an operational state. And so this is where our concept of Kubernetes operators have been introduced. And the aim is, how can we take what normally would have been done by system engineers and infrastructure teams when certain things happen, like upgrades need to be performed or something's gone down, and create a codified, automated way of managing it. So in this case, we've got XCD, which is a distributed data store, and in order for certain things to happen, there's different states. So as an event loop, the operator is looking at the current state of the system and deciding what actions need to be performed. So in this case, it's observed that there's 2 running nodes, and they're running as different versions, which is unfortunate. What we want, and what our desired configuration is they should all be running 3.1, and there should actually be 3 nodes within our cluster to ensure that we are as a core. And so the operator knows how to get to that desired state because it knows how to configure and deploy our system. And so it knows that it needs to restart and recover one member. It knows how to do that recovery operation. It also knows how to do an upgrade. But more importantly, it knows, because this is what a human would do, that actually to do an upgrade, we should also probably take a backup beforehand, just in case anything does go wrong. And this is automated and codified within our solution. And so these operators define this knowledge and experience. And so they get deployed as a YAML definition, and so they sit there watching the state of our cluster as part of the cluster. The most important thing is that when it comes to people within our teams who want to be able to deploy MySQL or Postgres or SQL Server in a reliable, consistent fashion, they can use that object definition from Kubernetes. They can take the extension points created by the operator, in this case the XCD cluster, and just have to define the parameters which is unique for that team. So in this case, how many nodes do you need and what the version should be? When it comes to scaling up, we would increase the size, we would reapply and redeploy this object definition to the Kubernetes cluster, and then the operator would step in and figure out how does it go from where we are today to where our desired state is, all through this really nice, consistent experience from a development point of view. So the final part, which I want to cover, is like, what should we monitor now? So we've got all of our .NET code running, and Kubernetes is making that consistent. It doesn't matter whether it's Linux or Windows. The only thing that we need to specify is what node do we actually want that workload running on, and we do that via a node selector. Kubernetes is managing how do we make services available, how do we deploy and scale up our different components, no matter what type of architecture they are. But from a developer and an infrastructure team, how do we now monitor what the state of that is so we can start raising alerts? And so Kubernetes, again, has got some really nice extension points to make that easy. And so when we're defining our services, i.e. how our applications are available to other things within the system, we can define additional information, additional metadata that other services can use and build upon. So in this case, annotations. And we can find an annotation that Prometheus, a monitoring solution, should go off to this service and collect all of the metrics. And so we added a tag saying that when you're doing your scraping across our cluster, please include this service and this application. And so within our dashboard, it would automatically detect that as we deploy it, and then it would automatically update the configuration and the covers and include it within its scraping. And so what Prometheus does is it goes after all of the different endpoints, whether they're part of your application, which you can customize and expose your own metrics, or off-the-shelf exporters, which automatically publish data based on your CPU usage, or disk space usage, like your underlying node information, or very targeted things like MySQL operations. So what are the number of deadlocks within your system, or the number of transactions which are active, which are very targeted to that particular problem. Prometheus doesn't care. Prometheus just sees this key value endpoint, and it will go off, it will scrape the data and make it available for querying. And so we can then start building up our nice, pretty graphs. So in this case, CPU usage and CPU nodes, but we can build something a lot prettier by introducing Grafana. And so this will take the Prometheus data source as an input, and then you can build dashboards. And these can then be ultimately projected onto display monitors, and when things happen, they'll be alerted. What we also have in Grafana is the ability to raise alerts based on the data collected. And so if we see things going slightly in the unexpected ways, we can get Grafana to raise push notifications or Slack messages or emails or PagerDuties based on this data. Because we've got Kubernetes underlying this, when new things get deployed and new things get added into our cluster, they will automatically start being introduced into our monitoring solution. And so we don't have to manually intervene and manually go and reconfigure something. Instead, the state of the cluster is defining what that should be. So what should we be doing? And so where is this all heading? And what is the future of infrastructure and containerization technologies? So we have Linux, we have Windows. They're now consistent. It doesn't really matter where we're deploying our infrastructure because Kubernetes sees that as the same thing. We also have IoT devices and ARM. And so there's a really cool company called Resin, and these have the capability of having the Docker approach, the Docker workflow, but targeting IoT devices. So when we want to package up and deploy our applications onto it, we can deploy it directly onto an ARM device. I'm sure you would have kind of saw on the agenda, you've got Scott Hanselman and you had Alex talking about running Kubernetes on ARM. It's exactly the same thing we've been talking about today for Windows and Linux. It's just another extension point, and you just another selector that you make available. And for those watching online, there's videos down the side, I'm sure. We have SQL Server on containers. So now when we're thinking about how do we deploy SQL Server, we don't have to worry about going through the 20 different screens in order to be able to get it to run. That's all been done and a default configuration that we can build upon. And we can share that configuration between all of our teams and make it available. But why can't we do that for development time experiences too? Like, we've already got the Azure command line running as a container, so we don't need to install it. So how long is it until we have things like Visual Studio running as a container on our development machine so that we don't need to install it? We won't have to download 5 gig installation to spend 2 hours installing it in the hope that it hasn't corrupted anything else on our system. Instead, it can be packaged up and isolated using container technologies, both on Linux, now on Windows. And we've already started to see this trend. The next version of Eclipse is going to be web-based, i.e. the future IDE from the team is going to be web-based. And in order to deploy and run that, you run it as containers. Containers has identified everything that it needs to do. It knows how to install it, how to get it configured, and we can instantly get something working. And when we don't want it anymore, we just stop the container, remove it from our system, and it's gone for good with nothing left behind. And this starts getting us to a point where everything is being a container. All of our workloads, both long-running, our big data, our development teams, are all packaged up as containers. And because we're building these consistent experiences, they can be deployed anywhere. And with the case of Windows, they literally can run different types of workload for different architectures, all on the same operating system, which is fantastic and something which is going to make lives a lot simpler in terms of managing infrastructure. So to play around with this, we have Katacoda, so you can explore different approaches to building containers, managing Kubernetes, and all of the underlying things like how do you expose services. In terms of other talks, I mentioned Alexis tomorrow, just before lunch, which I highly recommend, and I think it's going to be awesome. He's the founder of Weave and also the chairman for the technical committee of the Cloud Native Foundation, i.e. people who look after the Kubernetes vision. So it should be a really interesting discussion. And also we have PubConf for those. Please go see Todd and Track.js for more information. It's going to be an awesome party. So finally, what have we discussed? So we looked at how can we build and manage and run containers. Like, what does it take to build a Windows container, and how is that different from building a Linux-based system that we may have experience of? We then explored Kubernetes. Like, what does Kubernetes bring to the party, and how does it look, and what are the benefits? Like, why having this orchestrator managing our infrastructure, how does that look from an operation viewpoint, and what benefits does it bring by having that abstraction? And then finally, a quick look towards the future. Like, can we have all of our workloads seamlessly running across different systems, all being managed by this single viewpoint of our control plane and our single source of truth, which is Kubernetes. So I hope you found something valuable. I hope you enjoyed it. If you want more information, please feel free to always tweet or email me. And with that, thank you very much. I hope you enjoy the rest of the conference.